So I've been working on a literary historical problem for the past few years now, which is sort of Emily Dickinson's fascicles, which, since I'm short on time, very briefly, a lot of her poems were discovered after her death in small booklets that she had hand-sewn together, but because of some publishing strife between some family members, basically, over the years, those booklets and their arrangement were lost. So it's sort of been the project of some more recent Emily Dickinson scholars to try to forensically piece that back together, and they've started to notice that there's some very discursive things that are happening because of those arrangements. So my project has been to take that literary historical problem and sort of use topic modeling on it to see if we can discover some sort of semantic narratives that have traced their way through the fascicle books. So when we look at a topic model, and so very broadly, this is a sort of computer program that we can pump thousands of texts into, and it can kind of get these groupings of words which are ostensibly semantically related, but not necessarily. It could just be a sort of stylistic correlation. But this is generally what you get. And a lot of what we also get is a sort of, it's just you could think about it as sort of a probability of these words tending to occur in texts. Thank you. So actually, the numbers that pipe out for a sort of average topic distribution for the entire corpus is a sort of really smooth distribution. And a lot of the times, this is sort of where the story of topic modeling ends. It's sort of we look at these words, list of words, and we look at their distribution through the corpus, and we try to sort of make some sort of proportional sense, or like, this corpus is more about topic 67 and those words, whatever that particular semantic association is. However, it turns out, as I've been working with topic models, the sort of real meat of the topic model is sort of at its base, if you think of it as sort of a tree structure going down. And at the base, of course, are the texts and the topics themselves underneath of them. And if you look at a text, this is actually what a topic distribution of a text looks like. And so I want you to sort of keep these things in mind as I talk about today, because what I'd like to discuss a little bit is actually how we can close read this big data and get some very meaningful information from that. And so if you're looking at a text distribution versus this sort of average corpus distribution, it's kind of obvious. So basically each colored bar here represents a certain topic. This is sort of like a fingerprint of meaning. You could think about it that way. And so what I've done is I've developed this really massive visualization to kind of help people spatially explore topic models. And I'm not going to be able to get to talk about that today, but there will be a link at the end of this presentation where you can download it online and you can use it on your corpora to explore the models, especially from a topic models perspective, but also from the perspective of a publication as well, which is where I'm going to get to. So I'm interested in how topics filter through publication arrangements, in this case, Emily Dickinson's fascicles. So if we were to do the same kind of thing for a topic model, the average corpus distribution, if we were to take the average of the topic distributions, in this case, this is Emily Dickinson's 21st fascicle out of 40, and we look at the top 5, we can see actually sort of semantic narrative unfolding. And the reason this is a little bit more unique, the topic distributions, than that sort of corpus average, is because we're getting closer and closer to the individual texts themselves. So, but the literary historical problem that I've been talking about is also sort of very material. The scholars are looking at it, they've noticed that poems sort of speak to each other, across each other from the same page. So we're going to look at 2 poems today. And as it turns out, the closer you dive down to this material object, the more interesting and unique these distributions get. So in this case, we're looking at the distributions across 5 pages of the 21st fascicle. And in this case, we're looking at almost like this topic fabric. And these are each individual poems and their top 5 topics. And there are some links, and we can trace them out. We can actually just pull them apart like the threads of a fabric, and we see this sort of topic narrative that unfolds as texts move through a publication. And so specifically, we're going to look at 2 poems from the 21st fascicle today, very quickly. These are 2 views from my visualization on a very low level. These are the actual poems themselves with the topic words reinserted, so in the sort of human context. And these 2 poems are actually talking to each other across the page. One's called They Shut Me Up in Prose. The other is This Was a Poet. And this is Emily Dickinson kind of navigating what she gets from prose and why poetry is sort of a very freeing thing for her. And so if we look at the individual poem, and we take out all the stop words, this is actually, these are all the topic words in the order of that Emily Dickinson has arranged them. And The interesting thing is, though, if we want to look at it from the perspective of a topic model, we can take the topic level text distribution, and we take the actual distribution of the word weights within the topics themselves, and we can sort of form this composite weighting if we just sort of sum them together. And so in the same Dickinson order, now we have a topic model's word and topic text level view of how important these words are in this particular text. And then we can re-rank them by just summing those composite weights together. So now we have a list of words in the importance of how important they are to the model itself. And so this is a sort of a very similar view to what we were seeing originally with the list of topics, but now we're having the topic words in the context of the actual text, and we know how important they are to the model. Okay. Critics and us, we just read text, we associate words semantically, there's some polysemy going on. So what I've done is, I take a view of a critic, and let's color code it in a very similar way. So these are the two same poems, and I've used the categories of the critic, the topics of the critic, to color them in the very same way that you were seeing for the topic models, words, and context. And it turns out if we just do a very simple frequency counting of those topics as they move across those two poems from left to right, we can see a sort of semantic narrative unfold in a very similar way to how it would unfold in a topic model. And if we're interested in taking those weights and providing a sort of composite weighting scheme, we can actually take, so here are all those human topics. I apologize, this is a very quick talk, but I'll go back very quickly so you can see them. So we have the imprisoners, the poet, prison prose, freedom poetry, and poetry source. So these are the categories of a particular Dickinson critic. And if we're interested in those categories, here's a view that takes a composite of the critic's weighting scheme and the topic model's weighting scheme, and now we understand through the lens of the critic how those words are important to both schemes, but in this case we're specifically looking at the categories of the critic. We can also take that and show another lens on it. In this case we're looking at the lens of the topic model's topics. So we have the information, we know that in this particular view, how important it is to the model, how important it is to the critic, but we're looking at the topic model's categories in this case. And we can make our own assertions from there. And in fact, when we look at this this kind of weighting, you had that one natural counting from the critics' categories before. Now we have a completely different view. And this gives us an idea of that topic dynamic as it moves discursively between publications. But in a very different way that considers why the topic model, the computer program that generated this model, thinks it's important. And I think that's all about what I want to say is, but the visualization, which really kind of helps to unlock and get down to this level, is available at this GitHub link below. You can come up and talk to me later if it's not clear. As well as the code sits in this GitHub that generates all those plot views. And you can just, we can talk on Twitter or email, whatever. If you're interested in kind of generating these views or close reading a topic model in this way, just get a hold of me and I can walk you through it. So, okay, thanks.
So I wanted to thank Marion for the introduction, thank Kimon and Marion for setting up this event and giving me this chance to present. My talk, despite the title, won't actually be a lot about mapping literature. And this, I wrote a software tool in order to do that over the fall, and it's called New York Walker, NY Walker, and I deployed it in the 2 courses I'm teaching, or 1.5 courses. One is co-taught with Tom Oakst, that are both based on novels about New York. So the software creates maps of New York City, or the content of novels about New York. But once I saw the actual name of this panel and the idea about what was the unifying element of this talk, I decided to switch up a little bit what I would be talking about. So I tried to think of the way in which New York Walker could work as an algorithmic form of reading. And answering that question requires that we first look at New York Walker's About page. So this is the About page. And the About page is one of the several algorithms that is driving the site, at least if we understand an algorithm as being a sort of routine, a set of steps that achieves a certain goal. So when citing New York Walker, according to the About page, or one of the specific data sets that make it up, the bibliographic entry is generated on the fly based on how much each student has contributed to the data set. Most of the data in New York Walker was made by students. So the software iterates over the database, catching each edition by each student and sorting appropriately. I'm not sure that the students care too much about this, but I definitely do. It's very important to me. And keeping the students in mind, then, I want to move to this schematic here we have of a sort of research question. The red dots make up a set of inputs of some sort, and then from those inputs we want to generate some kind of output or outputs. There's just one output noted here. In the case of New York Walker, we can think of the inputs as being either as a novel that's full of place data, or each instance of a specific place, or whatever. The actual way it works out is not terribly important, because what we're most interested in is in the output. And the output in the case of New York Walker is a data set that presents every instance of a place being mentioned in a novel, or some subsequent subset of that larger data set, like a page range, or places that are mentioned by a specific character, or things like that. But one way or another, in between the inputs and outputs is something called magic. And that magic is what most of this talk is going to be about. So it's clear that we need to have some kind of other nodes in the system, that to get from inputs to outputs, there has to be something else that's going on there. And what they are these nodes in the middle, the purple nodes. And they receive data from the inputs. And then each of those nodes does individual work on the inputs. Like, say, the input coming in is a string Big Apple. So the nodes in the middle do the work on that incoming string, BIG space APPLE, and they do work on that, some kind of work. They do work on that string in order to generate a reference from that string of text to a place called New York City that has a latitude and longitude, that has a link to a Wikipedia page, and so on, that has all this other data attached to it, at least within the system. That's part of the way the system is set up. And then these nodes subsequently send their work, so they receive this data, they do work on that data, change that data, and they send that data along to the output. Now, this image might be a little bit familiar to some of the people in the audience, and definitely to people up on this panel, because anyone who's done any machine learning before might recognize this as a schematic of an artificial neural network. So each node then is, in fact, a neuron, not just a node, but a neuron, receiving a series of inputs, doing work on them, receiving a series of inputs from other neurons, doing work on them, and then sending the subsequent data down along the chain. So this example, this schematic, is just one step in the chain, because the inputs just can get more and more complicated, and so can the outputs. And this is basically how it works for a lot of sort of stuff like handwriting recognition and so on. And I'll talk about that a little bit later. So in an artificial neural network, those purple nodes are called the hidden layer. And one of the ways I conceptualize about why it's called the hidden layer is because we don't actually know what it does, and we don't actually care what it does. Depending on what you're doing mathematically, you can think of the sense of it working over a polynomial. Each of the inputs is like x1, x2, x3, and each of them is weighted by a coefficient, so a1, a2, a3, and so on. And each of those nodes has different weighted polynomial, or different weights for those coefficients, and adds to this polynomial so that you get an output at the end. And the point is that the system is trained to take these inputs and give a kind of output that we want. So if you train the software to see, you train the software to see that string Big Apple and know that this time it's a reference to New York City, but this other time it's a reference to large fruit. And if the software reproduces that result, then you don't really care about how the hidden layer did it, because the important thing is the output. It's the results that matter, right? That's what we're here to do. And this is what gets reproduced in handwriting recognition. You train the handwriting recognition to know what the number 2 looks like by giving it examples, and then it just does some stuff to end up with saying this is the number 2 on the other end. So that magic is the hidden layer. And sure, as a programmer, part of my job is to design and improve the algorithm, sort of to deal with this kind of hidden layer. But I also do that in order to keep those algorithms more hidden. So you get a novel on one side, and on the other side you have a map of all the instances of places mentioned in the novel. And this is sort of the promise of something like named entity recognition. I'll feed it some text, the computer will do magic on it, and the outcome will be will feature reasonably good ratios of precision and recall. So it'll do a good job of saying this is a place and this is specifically this place and so on. But there's one huge problem with the schematic as I've indicated it here, because in my case, in the specific case of the way the New York Walker data set was built up, the hidden layer isn't hidden at all because it's actually students. And just like in an artificial neural network, my pool of undergraduates needed to be trained. I needed to train myself. I also was a neuron in this hidden layer, if you want to think about it. Yet I end up in this kind of condescending situation where I consider my students little algorithms, little neurons taking in inputs and generating outputs. Even representing students with these purplish dots seems kind of condescending. Talk about making so this is talking about making the invisible visible, as Marion mentioned back in the first panel. I don't pretend to have access to any great insight here, of course, but working on New York Walker with my students over the last semester has forced me to continuously wonder about the human process of generating a data set from a novel. So the end result is now I have this large data set, and we get 6 maps like this for 6 different novels. This one, for Age of Innocence, shows that there are around 160 distinct places that are mentioned in the novel, and there are about 650 total instances that are mentioned. So the algorithms, that is the students, 4 students specifically, got us here, and we can think about how their invaluable efforts were a necessary form of reading, but a focused, trained kind of reading. But then I look at this map and I find it kind of boring, largely because the algorithmic reading that got us here still doesn't tell us a whole lot about the text itself. But that's also the beauty of New York Walker and why it's called what it is. It iterates and moves, but also importantly, it also exposes these iterations. It makes, again, in Marion's words, the invisible visible. So the hidden layer, just to bring the point home, is in this algorithm is these students, and their labor then is carried over into the next iterations, which is where they extract the data, look for patterns, and then go back to reading the text. They iterate over the data, and then they iterate over how they're reading the text in order to try to understand why these geographic patterns exist for their final projects, or then I'll do the same for future publications, etc. So I think I'm out of time.
45 seconds.
Okay, so I can quickly show just this is a map of just the places where the bubbles are sized based on how frequently they're mentioned, and then I tried to do a little bit of interpretive stuff. Like this is places Newland Archer mentions before he gets married and places he mentions after he gets married, so maybe his life is a little bit more interesting once he's married, but that goes against the reading of the novel and blah, blah, blah. And thank you. New York Walker is vaguely live. The URL is right there. And the slides are much less live because my FTP client is slow, but they'll be up in a couple minutes too. Thanks.
Thank you.
So what you didn't see in that talk about topic models, can you guys hear me? What you didn't see in that talk about topic models is that when you do topic modeling, you frequently get a whole bunch of junk topics. In fact, you'll get topics that just are all function words. You'll get topics that look indecipherable, that have no meaning whatsoever in terms of completely the opposite of what you saw with these topics here that are nice and meaningful. And that happens every time you do topic modeling. And so there's actually a lot of work that goes into figuring out, what words to exclude so that you get useful topics. And so what I work on now is statistical ways to identify interesting topics before any human had seen them. In very much the same tradition of mathematicians in the 1970s, where they were using computers to try to prove mathematical proofs, right? They would get computers that generate tons of theorems, but they couldn't look at them all. So they couldn't do much with that. So they had to teach the computers to generate and give them interesting theorems. And so I'm doing the similar kind of work with trying to teach a computer to generate interesting topics rather than just gobbledygook topics. But what I'm going to talk to you about today is something much simpler. It's seemingly much more straightforward, but actually is much more difficult, maybe, to do. And that is, I'm going to talk to you about counting words. So everything that you've seen here probably involves algorithmic word counting of some version or another. Everything you do online frequently involves some version of a computer looking at what you wrote and tokenizing it, breaking it up into words. And it seems like this process is really straightforward. It seems like it should be the easiest thing to do. In fact, it's one of the most difficult things to do, and that's what I'm going to tell you about right now. So the work I'm going to read comes out of my thesis. I feel safe that no one has read this because no one ever reads MA theses, so it'll be in the world, at least in this form. So consider your ability to recognize human faces. We usually have no grounds for confusion with faces. Either we believe we have seen one on the subway, in a window, in photographs, or we haven't. Note here, I'm not talking about recognizing specific faces. Rather, I'm just considering our capacity to recognize a face as a face. See, there we go. But for the case of human faces, we usually tend to agree, even for faces we've never seen before, and even if we are unable to articulate a specific definition of faces that doesn't invoke other non-numerical concepts like eyes, nose, and so forth. The identification of a face, for example, is achieved in a very different way by your smartphone than by you. I say this, we say this, even as we immediately recognize that what consists of recognizing a face for a computer and for myself are so different as to be radically different activities performed in radically different contexts. A computer recognizing a face, if we think to say this at all, is merely an acknowledgement of the placement of a box around the image of your face as I snap a picture of you. My recognizing a face, is when I see you walking down the sidewalk and stop to say hello. Yet once we apply a linguistic description of recognizing a face to something a computer does, we begin to ever so subtly redefine exactly what the phrase means to us. This new meaning seems to glob on to the other meanings and contexts we associate with the linguistic phrase. On one hand, it is precisely the malleability of language that allows us to repurpose a phrase like recognizing a face. But on the other hand, the flexibility of our language tends to muddle our thinking. Even though we realize that a phrase like recognizing a face means something very different, when we attribute the concept to a computer, we still tend to treat a computer as if it does the same sets of tasks that we do, even if we are unclear exactly as to what tasks we are doing. We say a computer drives a car, and it does. But its doing should not be confused with what we mean when I say, I drove a car. While we appreciate that there is a difference, our linguistic description does a very poor job of articulating what that difference is. While the above example may seem a bit mundane, it usefully illustrates certain misconceptions that tend to crop up whenever we use the sentence, the computer now does task X that was previously performed by humans. Now, there is a tendency by some to believe that it is much more difficult to recognize an image than to identify a word, but such claims depend almost entirely on the context being considered. Okay. We do not need to understand the meaning of to be or not to be to agree that this line of poetry is 6 words. But if I were to say this line was 7 words, you would not doubt my ability to identify words, but assume I had miscounted. To question one's ability to identify words is to question whether one knows how to play, say, the word identification game. And we usually don't do this. This is an important point. The kinds of mistakes that we assume are possible for a human to make will not be the same as those we think possible for a computer to make. Furthermore, we expect accounting for any conventions we establish regarding various special cases, that if you and I both count the words of this paper, we should get the same number. Contrast this case of human word counting with the situation of a computer. No 2 word processing programs compute the same word count for any text more than a few pages long. Which, I don't know. I think that should come as a surprise to you. So go home, use OpenOffice, use Microsoft Word, use Apple Text, put the same essay in, make sure it's like more than a page or 2. I guarantee you'll get different answers. That was very surprising to me. But in hindsight, of course, it makes perfect sense. This is because each program uses a different algorithm to identify words, and each of these algorithms makes different assumptions about what gets counted as a word. That we assign different possibilities for error for a word count performed by a human and an algorithm suggests that these tasks are very different, despite our inclination to use the same term for both. The computers identify words in a very different way than we do, but that we treat a word count obtained algorithmically to be good enough of an approximation so that we can use these results as if we had obtained the words by counting them ourselves. We may check our algorithm in several ways. As a programmer might, to see the algorithm gets the same number of words that we do, and make changes in the code if the algorithm and our counting are ever in disagreement. Yet it may very well be that the text we use to test our algorithm's ability to identify words does not contain the particular instances of language usage that would cause our algorithm to disagree with our word counting. This concern is exacerbated by the fact that we cannot pragmatically perform a word count for a very large corpora, so as to check the number with the count obtained with a computer. Thus, our uncertainty of an algorithmically produced word count seems to depend on 1, our doubt regarding the ability of computers to recognize words as words, and 2, the pragmatic limitation we have of not being able to perform lots of word counts of many texts ourselves. So to be sure that our check of our computer-generated word count is correct. How much time do I have? One important thing I want to point out here is that the Brown corpus is frequently used. It was constructed in the 60s. It's like the gold standard for all sort of tokenization programs. It's used because it's believed by computer scientists and many others alike that it was done all by hand with humans. But in fact, that corpus was constructed, 77% of it was constructed through an algorithm. So even here, the first corpus that's used as a gold standard for all tokenization programs was already mostly done by a computer. This is very different than our sort of like mental picture, where we imagine programmers comparing their results to what humans did. In most cases, there is nothing to compare what the computer did to. And so you have to, in fact, compare the computer to other algorithms that ostensibly do the same thing. So it's computers comparing computers. And that's how you obtain correctness. And that's how it's done for tokenization schemes. There is no gold standard that wasn't created by a computer that's millions of words long. Let's see. If you were going to do the same task for a human, interestingly enough, you would end up doing the same things that you do when checking algorithms. You'd have a bunch of people in a room. You'd have them maybe go through carefully line by line and count words and assign parts of speech and everything. But in order to identify who is correct, you'd compare all the results. And if the results were not the same, you'd have the humans go back and redo the task until they got the same number of words, which is precisely what you would do with algorithms. So interestingly, this points out, this suggests that the idea of a word count being stable as something that really exists in the world as something that actually probably is false. And this has tremendous implications when you think of word counts being used to do everything from identify spam mail, not just word counts, but the identification of words. When you think of that task being used to identify spam, being used to identify potential threats, right? There's a newspaper article, and I'm probably just out of time, so I'll end here. There's a newspaper article. Yep, there you go. There's a newspaper article just a month ago that talked about IBM and the use of metadata for refugees as a way of deciding algorithmically who were threats and who were not. Well, part of using that metadata is tokenizing words. So this, in fact, this process of making sense of tokenization and how words are identified by computers has implications that far extend, far-reaching implications. Thank you very much.
I wanted to mention the Henry James Review article, which is largely what this talk is from, partly because I use it as an example to prove to my colleagues that it's the end of the world. When you get a Henry James Review article with graphs in it, it's the end of the world. So Henry James notoriously changed his style from early to late. I'm going to rush through some of the early parts so I can get to a piece of early and a piece of late James, and I'm going to try to persuade you that you'll be able to tell which one's which. But in any case, he notoriously, his late style is so different from his early style that people won't read late novels, and other people won't read early novels. Editors will pick the original version of an early novel and reject Henry James's massive revisions for his collected works. So the Norton Critical Edition of The American is based on the original publication rather than the 6,000 word longer one written 20 years later. So the question is, can we figure out whether the argument that dictation, which is the largest, the main suggested reason for the change in James's style, is that he had carpal tunnel problems, and he went over to dictation about in the middle of his career. So the question is, can we figure out whether that's true or not using computational analysis? I'm going to skip this. This is a little technique called cluster analysis. You don't need to understand what it's about, except to note that the closer the texts join together by a line, the closer to the left they are, the more similar they are. And what I've done here is just to pick novels written before 1882 and novels written after 1882 and look at the frequencies of the 900 most frequent words and just compare how all those 900 most frequent words are used in these texts. And what it shows us is that the early novels separate radically from the later novels. You see how far you have to go up to get from an early novel in that top cluster. You have to go all the way up to the top, back down to get to a late novel. So early and late are extremely different. First, now I've stuck the middle novels back in. I put the novels between 1881 and 1901 back into the mix. And the reason Maisie knew is underlined here is that it's known that James started dictating somewhere in the middle of what Maisie knew. Okay? The outcry is obviously in the wrong place. You see it's a 1911 novel, but it shows up in the 1896 to 1899 group. What's weird about that? It was a play that he rewrote as a novel. So there's a reason that it might be strange. But in any case, what this little graph shows is how rigidly chronological James's novels are. Here's a strange-looking graph, but very easy to see what it means. What I've done here is I've taken words that appear, I've picked 18 novels, novellas, and stories from the early period and 18 from the late period. And I've found words that are at least 3 times more frequent in one of the periods than the other. So words that are 3 times as frequent in the early novels as in the late, ones that are 3 times as frequent in the late as in the early. Then I've calculated the entire frequency of all those words combined in texts from the very beginning of James's career to the very end. And none of these texts that are graphed here was used to make the distinction, right? So these, I've taken the ones I used to make the lists, I've thrown away. These are new texts. And what they show, I've multiplied the frequency by -1 to make the one set of words show up on the left so they aren't overlapping. But what you can see is a very regular development in James's career. He stopped using his early words and he started using his late words. And right in the middle is Maisie. And there's nothing there to show any kind of radical shift when Maisie happened, right? So that's the first piece of evidence. Doesn't suggest that starting to dictate is what caused his late style to develop, because the development obviously starts from the very beginning and goes to the very end consistently. But what if we look at Maisie itself? Can we see maybe something inside the novel as James is writing part of it and then starts dictating? It's not an unreasonable idea that he might change, that his style might change when he's speaking instead of handwriting. So what I've done here is I've coded these. The numbers are in chapters where it's possible that the shift to dictation could have taken place. And we know this basically very quickly because it was being serialized. So we know that some chapters had to have been handwritten because of the date when he first hired his first typewriter, as they were called back then. So the numbered ones, the regular Arabic numbers, are chapters in which it's possible dictation started. Single word titles are chapters before that, and hyphenated word chapters are chapters after that. Now, if you're looking at this graph, do you see an obvious decision about where handwriting stopped and dictation began? Well, maybe if you're really generous, you can see a suggestion that something about this bottom group looks like it's late in the novel. Right? There are lots of single Arabic numbers and hyphenated numbers. But you've also got chapters 3, 20, you've got chapter 10, 13, and 14 down at the bottom, they're an outlier. We could throw them away. So at best, you could imagine a kind of vague possibility that that somewhere after chapter 17, well, sorry, after chapter, what's the lowest chapter in the bottom group? 15. The problem is that chapter 17 is up there in the other group, along with the earliest chapters in the novel known not to have been dictated. So again, not much evidence. What if we just chop it up into sections and ignore the chapters, because the chapters vary in length? Well, it doesn't look very satisfying. You've got chapters 1, 2, 5, 6, 3, 4, and 10 in the top group. And then you've got 7, 16, 8, 20, 21, and 22 in the middle, and then 9, 11. So it doesn't, there's no obvious suggestion of dictation causing this. Well, maybe narration is different from dialogue. Does it seem reasonable to you that if you're speaking dialogue aloud, you might change the style more than if you're speaking narrative aloud? Turns out the dialogue is problematic because it varies in amount, and the amount by each character varies a great deal through the novel. So I decided I would just try the narration. Again, not really a very satisfying split. You could say maybe after section 8, which is about chapter 17, by the way, maybe there's a hint. But this is in fact the only analysis that shows this split. If there really were a radical shift caused by dictation, every analysis you showed would split the two parts. I'll come back to that in a second. What if we try things that are not as interesting as words? Sentence length is notoriously ineffective as a way of identifying authors or stylistics. But it's possible that longer sentences or shorter sentences might be a characteristic of dictated text. Well, do you see a change point? I mean, I guess you could call this a change point, but the problem is all it does is go back to the beginning, and then it drops off again. Where would you say the change happened? Maybe there, maybe there. I don't know where. So again, and the problem is that all of these different features show possible breaks, but they're not in the same place. So we get no consistency, we get no evidence. So here's the rest of the punctuation marks. James apparently was very good about speaking the punctuation as he dictated. Apparently he only ever dropped the period. So what about long and short words? Is it possible that dictating might shorten or lengthen your words? Might you use shorter words spoken? Well, if you do, where's the evidence? Where's the chop? We know that the dictation couldn't have started before section 8 because that much was written and published before he started using a typewriter. And we know for sure that the last 5 or 6 sections had to have been dictated. So where between 8 and, say, 12 is there evidence of a radical shift? In none of these graphs do you see anything that suggests that. So the argument that I make in the article is that even though this is very tempting, James's late style is always dated right about to the late 1890s, right about the date of what Maisie knew, and that's right when he started dictating. But the fact that it happens at the same time does not mean that it was caused by it. And we've seen that gradual chronological change in James. We've seen no evidence that the novels written right around Maisie alter. In fact, the novels between 1896 and 1899 group together, even though the 1897 Maisie and the 1899 Awkward Age were dictated and the others were handwritten. So very quickly, here's a very fascinating, it's one of the rare pieces of Henry James' manuscript. He apparently destroyed them. This is the beginning of chapter 17 of What Maisie Knew. There are exactly 2 chapters of What Maisie Knew that in existence in typescript. So it's really tantalizing to imagine, well, maybe this means that James saved these 2 chapters because they were the first 2 chapters he dictated. And it is about the right place. There are 2 problems with it, which is one of the things that makes this kind of work so much fun. It's annoyingly problematic. If you'll notice up at the top right corner, there's a page number typed. what does that suggest to you? Does that suggest a scenario in which there was a handwritten manuscript up to this point, now replaced by a typewritten manuscript? No. He had to obviously have typed pages before this one. But what's even more annoying is the date. July is roughly when he had to have been finishing the novel, because it was published in September as a novel. It finished serialization, I think, in August. So it's not possible that he could have been dictating chapter 17 way back in the middle of the novel, clear in July. So even though this is very tempting and serendipitously odd, also you can't see it here, but there's an erased penciled note up in the top left corner that says something about X paid to McAlpine, who was his typist. But you can't read it, it's been erased. You can read Henry James's signature underneath it, all in pencil, all erased, but you can't tell what it actually says. What we would really like, of course, is a note that says, first 2 chapters dictated to typist, Henry James, right? That would be a nice answer, but it's not true. All right, I'm going to just do one quick thing to show you that these techniques do work when you have a real difference. So here's an authorship difference. Robert Barr finished Stephen Crane's last novel. That's how well Barr's chapters are distinguished from Crane's chapters, even though Barr had the outline, the plot, all the characters in the setting, and was trying to sound like Crane, right? Can't do it. Here is the Goldstein section of 1984, that theory of oligarchical collectivism that's in the middle of 1984. Here's what those word lengths do when you have a bona fide real change, right? And you would think this have to happen. What's inside that political tract is lots of polysyllabic words about oligarchical collectivism, right? This is the end of The Handmaid's Tale, where she shifts out of the dystopian novel and jumps forward into the future a couple of 100 years to an academic conference about The Handmaid's Tale. And you get radical shifts. There's no question where something happens in this graph, right? Compare it back to those ones we were looking at, hoping to find a difference in punctuation or word length. I'm going to skip this. This is what Henry James said when someone wrote to him and said, "Mr. James, doesn't dictation change the way you write? I can be trusted, artless youth, not to be simplified by any shortcut or falsified by any facility." So I think maybe we should trust him. Maybe he was right. I don't think we have time to look at the late and early, but try it sometime.
Thank you. Franco Moretti is the great-grandfather of distant reading. And when he came to NYU, I think to talk possibly a couple of years ago, 1-2 years ago, he said this is a field that has to prove itself soon. It's been going for quite a long time. It has to generate new readings of novels. It has to do something really interesting soon. And I think we've had some really nice responses to that challenge on this panel. And one thing that really strikes me is that what I think we're getting towards from these algorithmic ways of reading now, one thing that's come out of, I think, all of these papers is not necessarily so much a new reading of the novel, something we didn't pick up through close reading that can be sort of added through distant reading or algorithmic reading techniques, but rather an analysis of the processes of reading and the processes of writing that these algorithmic ways of engaging with literature allow us to ask questions about how we read and how machines read, how writing processes take place. So for me, this provides some really interesting responses to that important event a couple of years ago. We have some time for questions, and we have a microphone somewhere.
Hi, 2 questions on technique and process. One, when you're making up a graph that uses color, do you consider people who are colorblind reading them?
Yeah, certainly that is something that I think people are very much growing aware of. In my case, I'm trying to get this stuff out so as fast as possible, but it's certainly a concern. And again, color doesn't actually translate, as David pointed out to me, to print publication. It's a big problem. So when you do rely on color, then it's probably going to be digital-born scholarship. But there are other concerns as well, like you're pointing out.
The other question is in terms of finding places in a novel which is fictional. The computer reads it as an address, but as we know from television, for instance, the cops were sent to 700 West 75th Street. New Yorkers know that's in the Hudson River, but somebody reading it in California thinks it's a real address. So how do you consider that part of your algorithm to make sure that the computer is smart enough to know what's a real address, or telephone numbers, 555.
What you're describing, first off, just quickly on the color thing, because color is extremely important in cartography as well, and it's the degree to which people who make maps and have the audacity to put maps in public but actually don't know the first thing about color is persistently astonishing. But there's good websites, Color Blender, I think it's called, that, what's that? Yeah, but it's called Color Blender or something? Color Brewer, which it does a bunch of things. You can give, like, I want 5 colors that are distinct from each other, and it gives them, and you can set for, okay, but I want these circumstances and these circumstances. So the website was created specifically for mapping purposes, but it can be used in any kind of visualization type of thing. And these palettes should be like built into PowerPoint and built into Keynote and things like that. As for the places, what you are describing is precisely exactly why I don't have the computer do the work. I have students do the work. I skipped a slide where I talk about. So one of my students, she coded, there were references to Brasilia, and she coded that as just a different name for Brazil. And, she just didn't know. So she made a mistake, and I can go in and I can fix that. But in a computer, in the meantime, there's this one sentence from Dos Passos' USA where there are 5 places mentioned in it. The computer found one of them, and there's a reference to a president of Mexico that the computer insisted was actually a place. So the computers have to get kind of far too. But because people are coding this sort of stuff, then they can code for that uncertainty. And one of the things I've really tried to explain to my students is to be okay with that uncertainty. So like in Age of Innocence, Skuytercliff is one of the houses, and it's pretty clear that Wharton made this place up. But it's still mentioned, so we still record it, we just don't add coordinates for it. So something like 700 West 15th Street, we would encode it because it's in the novel. It has semantic importance regarding the novel as a whole, but we don't presume to then put it on a map in some kind of way. If it were Chicago, then we could just sort of say, well, 700 and the edge is 600, so it's one more city block, so it's a quarter of a mile farther down, or something silly like that. But yeah, that's the important thing, and that's why the map is never the finished product. You always have to go back and then reread it, because you have to keep in mind that these are products that have semantic and aesthetic value and appeal beyond just being a data set.
The other thing that not mentioned yet about color, in addition to the problem of color blindness, is that color saliency is crucially different. I mean, I was marking early and late words in Henry James using blue for late and red for early, but they aren't equally salient. So the early passages looked more early than the late ones did. So I had to shift from doing that to using the same color, but switching from late to early. And then, of course, I had to print it in a print journal. So then I was trying typefaces, and the same problem happens. That script typeface or the sans serif typeface, they have different meanings to a reader. So the visualization is very, very complicated thing to get right. So I think that's something that there are a bunch of good design people working on it. My friend Sten Rooker is a big person in that field.
I would add, so visualization I mentioned, but I wasn't able to show to you today. Because of that very same, that salience issue, what I do is I rely on highlighting. So we're be able to interact with this thing. So this is a digital born object with the mouse. So once you highlight over it, move the mouse over it, then what I do is I highlight every instance where that particular topic in this case, or that particular color occurs throughout the visualization. But of course that's lost if it was a print publication, print visualization as well.
This came up at an earlier panel, actually. I'm concerned about knowledge as private property. I would like to be free, and newspapers, for instance, a lot of the old newspapers in the United States seem to be on private. You have to pay to. They're not even. I don't think they're on NYU. Even if you're a student here, I don't think you can get them. Also, genealogy sites you have to pay for, but there's a lot of really important information on them that's privately held. Maybe this is also related to the distinction between privately owned software versus open software. Maybe that's the same issue. I was wondering if people had comments about that.
Sure. Yeah, so I mean, this is it's been a big problem for digital humanists, and this has been a very big problem for digital humanities scholarship, right? I mean, one of the reasons beyond the fact that I really enjoy and have enjoyed looking at 19th century American literature, it's a very convenient, way of accessing that material. But and I've worked actually with the Google Books team, so I know all these sort of legal ins and outs, and who knows how exactly they're going to play out with this new decision that has come out recently, where they are actually able to, I think, embark on their project of digitization as long as it's sort of a limited view, limited access. However, the Hathi Trust, which is a private organization, right? So they have been accruing all these digital texts which are inside of copyright and private access, but what they have been able to do is, and this is out of the University of Illinois, Urbana-Champaign, they have a center there, and this is all freely accessible. So if you go to the Hathi Trust site, they have an API where they give you access to the sort of metadata of those texts at the very least, and I think there's some very limited access to the text as well, so that'd be something to check out. And that's been one way of sort of getting around those very rigid legal barriers at the moment.
I would just add to that if you're using text from the Hathi Trust, Hathi or Hathi, I don't know. It took me I don't know 2 months to figure out why their emblem was an elephant. You all know? No. That's the name of the elephant in the Jungle Book. That's what Kipling calls elephants. Anyway, they remember. And they remember things, right? Elephants do. Those texts that are in that collection are most of them not tokenizable with any degree of accuracy at all because they have line end hyphens. As many as 5 or 6 per page. In a 400-page novel, that's, what is that, 2,000 errors right there. So I'm a little dubious of giant projects done on these very messy texts, and many of them are in dialect, so that the tokenization is, I would say, I like to tell this to computer scientists because it makes them so mad, it's impossible to tokenize correctly. It's questionable whether a human can do it, but it's impossible for a computer to do it. In fact, I ran a part of speech tagger on a 1,000-word passage of a dialect novel, 50% error in part of speech tagging. And it was all because of tokenization. All of those words with apostrophes at the ends of them where the G is missing in an ing word, or the because is cut to cause with an apostrophe. It's hopeless. You have to do that stuff more closely manually.
Yeah. I have a question for you, David. And you're very kind of orthodox in working with words,
Yeah.
right, and word lengths, and you kind of answered it. But I was wondering, the Henry James issue is, I wonder if phraseology and lengths of clauses or use of clauses, like if someone's actually speaking, that might be where like exhaustion kicks in, which is different. And it seems like you're not doing it. If you could do it, you would do it. And if that's just a computer science limit, or would that not show more than the word length is showing?
It might, but the fact that you saw in that graph of the words, all those graphs that showed how you could split early from late, early from middle from late, and lay out the chronology, all that's based entirely on words. So we know, in fact, that the chronology can be identified using word frequencies alone. So yes, syntax would be better, but do you really want to run a parser on this sentence? What it all amounted to at any rate in the middle here was that Mrs. Assingham would be keeping him quiet now while his wife and his father-in-law carried out their own little frugal picnic, quite moreover, doubtless, not much less neededly in respect to the members of the circle that were with them there than in respect to the pair they were missing almost for the first time. No, I
German moment.
yeah, and that's late James, and that's why some people don't like it. But yes, I've done n-grams, so I've cheated a little bit. You can get a little bit of syntax. But what's remarkable about the late James is this very stuff, this self-interrupting internal interruption in the sentence. But it's also, weirdly enough, combined with an increased use of slang. So you get these really strange dialogue sentences that are 150 words long with 3 parentheses and 2 dashes and 5 slang words in them. It's totally dislocatingly weird.
That's great that you, because that's context out of close reading that you're
Yeah.
giving us too, which is to reiterate this importance that these things work really well together if done appropriately, and that there's definitely an enhancement.
Yeah, I don't
to
do
that.
distant reading, and you know, novel people, newbies like Franco, think they invented something interesting. But who was saying? Marina was saying that the film stuff goes back to the 1920s. Text analysis, algorithmic text analysis, goes back to 1884.
1887. If you
1887.
If you take De Morgan, then it's even 1850 or whatever. But you can do philology, and then you can say it's 2,000 years ago, right? But statistical, probably like 1854, I think. There's a point here. So when you asked, like, well, you could use phrases, right, as opposed to words. Well, or you could use like any kind of n-gram described in any way, right? You could use skip n-grams. You could do. So the problem actually isn't like, how can I find the thing that best gives me the results that I want? Because this is statistics, you can always find something that precisely gives you the results you want, with no error, right? So it's a tricky problem because it's not that we can't get it to fit. You can always get it to fit by careful selection of features that you look at, right? We could have this conversation, but I would say you can. If you're willing to do anything, skip grams,
if you're
phrases,
willing to cheat.
like, yeah. Well, but what counts as cheating, right? That's I think a really interesting question, right? Like what counts?
Well, I
as
don't
cheating?
think you can find things that are not there, even if you want to find them. So I don't think that you're going to find a split in what Maisie knew that shows where dictation took over. It is possible. I grant you.
Could make it.
It's
I
possible.
could make a split, right? Like just by choosing the right features.
But this is one of those cases where we can't find out if you're right after you're done, right?
That's right.
There isn't any way to know whether that's correct.
Yeah, but that's the problem.
Yeah.
Right? Because I mean, that's the issue.
I'm struck by David saying it's hopeless and there's no way of knowing whether you're correct. That seems like a good note on which to end, really. It's important always to maintain those realizations and skepticism, I think. But thank you for a really great panel. I'd just like to give our speakers one final round of applause.